Hello and welcome. In this video, we are going to take a look at a very interesting data structure which is known as a heap. Now before we go and understand what a heap is, I really want you to understand what a priority queue is, because a heap is essentially an implementation of a priority queue. So what is a priority queue? A priority queue is an abstract data type, okay? And this guy basically supports a few functions, and a few of them are get min or get max, okay? Another one is insert key, another is delete min or delete max. Okay, so let me elaborate a bit more. So a priority queue is essentially a container in which you can place many elements, and these might be integers, doubles, floats, or whatever you want. Now essentially it should support either a getMin or a getMax function, which will allow you to quickly get the minimum of all of the elements that you have stored within this data structure. And similarly, the max is used to get the maximum of all of them. And what is this insert key operation? The insert key operation is basically used to add another element into your priority queue, and it might be an integer, double, or whatever you're storing. And the delete min essentially means that you take out the minimum valued element from this guy and throw it away, and that's all. And then you do some internal reordering that is dependent on the implementation of the priority queue. So a priority queue is an abstract data type that supports a getMin or a getMax, and similarly a delete min or a delete max, and an insert key operation. Now coming to what a heap is. So a heap is essentially a data structure that allows you to create a priority queue, and it supports this getMin and getMax operation in O of 1, which is constant time. It allows you an insert key operation, which is logarithmic, where n is the number of nodes that is currently present inside the priority queue, or the number of elements, and delete min or delete max also in log n time. And this is really good time complexity over here. So this is the motivation for studying a heap. And where do we use a priority queue? If you ask that question, then obviously there are some very common applications of it, such as in the well-known graph algorithm like Dijkstra's algorithm. Then you've got Prim's algorithm. All of these guys make use of the priority queue, and you may use it in any of your own algorithms as well, in any competitive programming contest or any such thing. So coming to what a heap is. Well, a heap is nothing but a tree, but it is not any tree, okay? It's a binary tree, and a special one at that. Not just a binary tree, it's a complete binary tree. So what is a complete binary tree? So a complete binary tree is a binary tree which has all of its levels fully filled except for the last one. And all of the nodes that are present in the last level are present as much to the left as possible. So this is a complete binary tree, but this is not a complete binary tree, because this guy could have been over here, so it's not present as much to the left as possible, and therefore this is not a complete binary tree. But this is a complete binary tree. Again, this is not a complete binary tree, but this is a complete binary tree. Alright, so what are the conditions for a complete binary tree? All levels, pardon my handwriting, all levels fully filled except last one, and all nodes in the last level are present as much to the left as possible. So these are the two conditions that are required for a complete binary tree to exist. So now we can actually take a look at another interesting property of a complete binary tree. Okay, so say suppose you begin numbering the nodes as like starting from 0 and at the root, and move towards the left as you number and towards towards the bottom. So in that way you would number these nodes as something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is how you would number a complete binary tree if you move this way and downwards. Alright, so this leads to a very interesting property, and the property is that if you take any guy over here, any node, okay, you're going to have the left child as 2 times I plus 1 and the right child as 2 times I plus 2. So let's check it. Let's take I equals 4. Then we are going to get the left child as 9 and the right child as 10, which is equal to 2 into 4 plus 1, 2 into 4 plus 2. So you can check it. This is 4, 9, 10. Now this is an interesting property, and it leads us to like implementing this binary, this heap, not as a connected set of nodes but as an array. And let us see why that is the case. So say suppose this is your array. You have 15 nodes at the moment, so you can make 15 boxes, and then you can simply treat these indices themselves as the nodes. Alright, so the node with an ID of 0 is present over here, the node with an ID of 3 is present over here, node with an ID of 7 is present over here. So now if you need the left child of this guy, it's very easy to get it, as you can simply get the index, multiply it by 2 and increase it by 1, and you've got 7. So this guy is essentially the left child of this, and the right child is this, right? So we can simply have a function which returns the left child and takes an I as return 2 times I plus 1, and another function as right child which takes a value I and returns 2i plus 2. And this array and these two functions would essentially help us to emulate this structure as a whole. Why? Because it is a complete binary tree. If it was not a complete binary tree, this would not have worked, but since it is, we can do it with the help of an array and these two functions. So this was the basic layout of a heap, and in the next few videos we are going to see how it supports the get max, get min, delete max, delete min, and insert key operations in the time complexity that it advertises. So yeah, see you in the next one.